Okay, let's talk about some basic electromagnetism. And, electromagnetism is, as the name implies, the marrying of what I guess scientists a really long time ago thought were two completely unrelated, um, forces of nature, electricity and magnetism. Although I have heard that sailors, when there were lightning strikes, would notice that their compasses would go all wonky. So, there might have been a hint that electricity and magnetism were related maybe before, you know, scientists actually started to work with them, guys like Ampere and Michael Faraday and so on. So it turns out that electricity and magnetism are related to one another. And we'll start this in maybe its simplest form. And that is the fact that a current carrying wire has a detectable magnetic field around it. So if we imagine this is a piece of wire that is carrying current, positive to negative, okay? If you place compasses around here, you will find that there is a magnetic field swirling around this, okay? And I think maybe the easiest, it's a little hard to kind of imagine how this works, so it's like a 3D scenario. So what you have to do in order to visualize what's happening here is you have to realize that, this comes behind and in front, okay? So it coils around and around and around. Now, in order to make that make more sense from someone's perspective looking at this from the side, and I'll explain why the magnetic field goes that way in just a second. So this is representing the magnetic field around the current carrying wire, right? Current is traveling that way, okay? So there's I. Our current is traveling this way. B is our magnetic field. But the best way to imagine this is that this is embedded into the page, and therefore the magnetic field goes back into the page and then comes out in front of the page, and that the wire itself is just laying on the piece of paper, okay? So imagine the wire's laying on the piece of paper, then what you would see is the magnetic field is pointing away from you below, okay? So pointing away is going to be represented by little X's, and coming towards you is going to be represented by little dots. So it's like we've sliced this field right in half, and we're looking at a cross section from the side of it, okay? The way to remember what's away and what's towards you is imagine you have shot an arrow, like a bow and arrow, right? An arrow from a bow and arrow looks like, I don't know, this maybe. It's got this at the front, okay? So if you're looking at it from the back, you would see the tail feathers of that arrow going away from you, and they would look like an X. If you were standing in front of this arrow and looking at it, you would see the tip of the arrow coming towards you. Okay, so X's mean away from you, and dots mean toward you, okay, in the plane of the paper. Now, how we know which way this field points is using the right-hand rule for this, which basically says if you take your thumb, I'm going to try to draw your thumb here. You point your thumb in the direction of current flow, and then you wrap your fingers around the wire, okay? They will point in the direction of the magnetic field, okay? And just to remind you, if we have, say, a north and a south pole like this, magnetic fields always point which way? Out of which and into which? Just remember what would happen if I put a compass in here. Which way would it point? Yep. So we'd go like this. Magnetic fields always point from north to south. You have to know that. That's super important. Okay? So what that also means is, if I were standing in here and looking at this, would this eyeball be seeing arrows? Or would this eyeball be seeing X's? Arrows, right? It's coming towards. Okay? So north behind, south in front, if you want. Okay? And we'll look at that again in just a minute. Okay, So the right-hand rule says thumb in direction of current. That's your thumb. Fingers, how do I do this? Fingers coiling around. I hope this ends up looking like a hand. Fingers coiling around the wire. They're supposed to be fingertips. Okay, and then the wire is here, right? Okay, so in other words, you are going to see, these are the tips of your fingers, right? This is the direction the magnetic field is pointing. You're going to see that. So imagine you took your right hand and you kind of grabbed it around the wire with your thumb pointing in the direction of current. Well, your fingertips are going to show you which way that magnetic field goes. Okay? I'm just going to do a top view of this. So I'm going to imagine we're looking at this wire from, say, end on. Okay? So you would see the wire in the middle. Okay? From this guy's perspective, if you have a look over here, from his perspective, he's going to see current now coming towards him. So the current is coming towards him, so we're going to represent current as a little dot. Okay, so I'm going to draw a little eye here to remind you that this is now current, electric current coming towards you. You're viewing it from this end. Okay, so now imagine the current's coming towards you, aim your thumb up, and you're going to see that the field points around like this. Okay, so if I were to take a bunch of compasses, or to place them around this wire from this perspective, what I'm going to see is all the arrows on the compasses pointing in the direction of that magnetic field all the way around. Okay, so this is what's going on here. This field is going like this. Michael Faraday explained it as if when there's a current flowing, there's a spiraling wind around here, and if we place compasses in that wind, these compasses get caught up in the wind just like flags. Okay, and those flags will point in the direction of that magnetic field. Are there any questions about this? So this right-hand rule, I don't know if it's right-hand rule 1 or 2, but this right-hand rule is very good for helping you remember which way these magnetic fields behave. And you will have to know that. You know, if the current's flowing this way, the magnetic field works around like that, and vice versa. All right? And remember, the compasses are pointing in the north direction like that. So something to remind yourself here too is that this is only happening while current is flowing. Current is not flowing, there's no magnetic field there. Okay? Now let's talk about something else. Let's imagine that we create a magnetic field. So one way to do that is to take a horseshoe magnet, and that will, sort of like the parallel plates we talked about in electricity, that will, as we saw above, build a more or less uniform magnetic field across here. Okay? Now what I want you to imagine, let's get your spatial reasoning going here, but imagine that you're inside here, okay, and you're looking at this field. Okay? Well, from the perspective of you, what you're going to see is you're going to see all of these arrows of the field pointing towards you. Okay? And just to remind you, I is the symbol for current, and B is the symbol for magnetic field. Current is measured in amps, right? We know that from before. Mag field is measured in Teslas. And in the other video, we sort of basically set up what Teslas were, but they're a measure of the strength of a magnetic field. Okay. So, let's imagine that we stick a piece of positive charge here, and that we shoot this positive charge into the field. How might we do that? How might we accelerate and shoot some positive charge into this field from the side? How might we do that? What's that? Well, I think the best way actually would just be to create some sort of strong electric field. Okay, possibly like this. Okay, have some way of injecting ions into here, which you can do. Okay, put a negative plate over here. Okay, like that. And if you think about it, pretty much you put, you know, some ionized, yeah, sure, hydrogen ions or whatever it happens to be. Anything really that has a positive charge, alpha particles, whatever, it doesn't matter. But these, if you put this under vacuum, right, and you put your magnetic field somewhere in here, you can actually accelerate charge, and some will hit the plate, but some will actually like come flying through, right, with some velocity behind it. Okay, this is kind of the more or less basic principle maybe behind certain particle accelerators. That's kind of their principle of operation, obviously much more complicated, but that's kind of the general idea. This will accelerate particles across it, and then you can actually create a beam of positive particles that you can then experiment on outside of this. Okay, so imagine this is the case, and this is some sort of magnetic field, and what we want to do is we want to see what this charge will do when it enters a magnetic field. And you know, the key thing here is moving charge and magnetism are intrinsically tied together somehow, right? So what happens here is as this enters the field, as long as it is moving, it will start to experience a force, okay? This brings up another right-hand rule, okay? This is a little bit different, but basically, you take your fingers and, you know, I'm just going to try to mimic what we have here. So you're going to point your fingers, you're going to put your hand open and flat, like a tabletop, and you're going to imagine your fingers are pointing in the direction of the magnetic field. So in this case, this is B. So your fingers are going to point in the direction of B, okay? So let's imagine here, here's your fingers. Try to draw this the best that I can. Oh, actually that's not right even, because your thumb has to point in the direction that that charge is flowing. So actually what you're going to see here is this, like this, okay, and then your thumb, that's your thumb there, it's going to point in the direction the charge is flowing. So these are your fingertips, right, facing towards you in the direction of the magnetic field. Your thumb is pointing in the direction of the positive charge flow. So we can actually call that I if we want, because I mean it's kind of like a current flowing that way. And then your palm will point in the direction of the magnetic force that that object experiences. So in this case, if you set your hand upright, your fingertips should be pointing towards you. Your thumb should be pointing to your right. Your palm should then be forced to point down. Okay, your hands flat like a tabletop. Like you're giving someone a high five, like wide open, right? Now take your hand, leave it like that. Point your fingers out of the page towards you, your thumb in the direction of the positive charge flow, and then your palm will point. That is not right what you're doing here. Look what I'm doing. It should look like what I'm doing. Okay? So you should be pointing your fingers at your eyes right now, and your thumb should point to your right, and your palm should be forced to point down. Okay? So this positive charge will feel a force in the downward direction when entering this field. Okay? So that is the direction of the force on this charge. And what it'll do is it'll start to react to that force and curl up. Okay? So what if I inject positive charge here? What if I take it and I fire it in this way? What happens now? Which way does the force point? You should get up, right? You should get up. The thumb points in the direction of the flow. The fingertips point out of the page. Your palm should be aiming up. So you should get this kind of a bend because the force, once it enters the field, will be up. Okay? Here's another question. If I take a negative charge and I fling it in there, Well, do the exact same thing you did before, exactly the same, except now the force is just going to be in the opposite direction. Okay, so if you fire a negative charge in there, it's going to do that. Okay? Yeah, but just like I just say, do it the normal way, and then realize if it's a negative charge, flip the force. That's all you got to remember. Okay, and just hopefully to make this a little clearer than my drawings were. Here's your first kind of right-hand rule for current flowing through a wire and the way the magnetic field coils around it. Here's the second one. So you imagine laying your hand, your fingertips are going to point to the direction of the magnetic field, thumb to the direction of positive charge flow, and then force coming up. So it's like 3 dimensions, right? Which makes it a little tricky. So far we've been able to kind of do physics in 2 dimensions. As soon as you get 3, it's pretty hard to represent on paper. But this is this, okay? So this is you looking at the front of the hand, and the hand has flipped over. Okay, so there we go. That's kind of interesting. Now there is a little bit of math here. So let's write down what's going to happen here with the math. Now, one thing that you need to kind of realize here is that these forces are 90 degrees to one another, so perpendicular to one another. So the electro and the magna components of electromagnetism are at 90 degrees to one another. And so what that means is that the interactions between, say, particles like this are strongest when these are traveling across a field. So in other words, if you, say, had something like this, let's say we had a wire aiming like this. Let's say we had current traveling this way in the wire. And let's say we also, on top of this, had a magnetic field that was pointing like this. Okay? So we have a magnetic field that's pointing like this. There would be no force present in this case because the current and the magnetic field are in the same plane. Okay? If you want there to be action, okay, these things have to be behaving at 90 degrees to each other. So in other words, if I take this wire and instead of traveling in that direction, it travels at 90 degrees like this. Okay, if we move it like that, now which way will force point on this thing? Well, you know, fingers pointing in the direction of the magnetic field. Okay, so in this case to the right, thumb pointing up, you're going to find force goes away from you into the page here. Okay, so your force goes away from you into the page. So the force on here is away from you. So we'll draw it as X's. But if I turn this to the side, right, if we put it in the direction of the field, we have nothing. Okay, so that's sort of important. All right, so when this is at 0 degrees to the field, we have nothing, and when it's at 90 degrees to the field, we have our full force going on. So the math on this works like this. Force equals D I L sine theta. So what does that mean? Well, it means that if we have a wire carrying current of length L, okay, length L, a current of X amps, and a magnetic field of X Teslas, and an angle of anything from 0 to 90, the magnetic force is calculated as FB. So FB equals BIL sine theta. So for example, imagine we have a 5 centitesla field with a 2 meter long wire . and a current, 2 amps going through it, with an angle to the field of 45 degrees, find FB, the force on the wire. So, pretty straightforward with a setup like this. 5 centiteslas, so 5 times 10 to the negative 2 teslas. Current 2 amps. 2 meter long wire. And sine of 45 degrees. What's the sine of 90 degrees? 1, right? So 90, if this were at 90 degrees to the field, this would just be 1. So I think you should get this. Does that make sense? Make sure your calculator is not in radians, okay? This is not a radians question. Unless this was given in radians, then you would do it in radians, but it's not, it's given in degrees, so rolling up, that's to deal with a current carrying wire and how it would interact with a field. The reason why this wire interacts with a field, right, is for the same reason that this, piece of charge or this charged particle would. You have to remember that what this is a whole bunch of positive charges in a row flowing through. So if you imagine on its own one single charge particle moving into here, well, it's going to bend away from you, right? Just by using that right-hand rule. So again, what we're doing now is we're saying, okay, instead of being a free proton or something like that flying into the field, we've now got protons, or we've got electric charge traveling through this wire, and the whole wire is experiencing the force that every one of these individual charges would feel. Okay. Well, the whole wire would tend to move because it would feel a force all the way along its entire length. Okay. The total force would be 0.14 newtons. Can you think of a way to make a wire move using this property? Imagine this. Let's imagine that you have a length of wire here in sort of like a cylindrical shape, right? So let's imagine that we have like a piece of metal that's round. Not sure why it keeps showing me the eraser button here. It's super disturbing to me. Okay, so there we have that. Now let's say we have 2 electric rails like this, here and here. So we're looking top down here, right? We have 2 bare wires, and we have a cylinder, a metal cylinder that can flow. And let's say we run current through here, right? Now the current is going to run this way and this way. If we were to now place this in a magnetic field that were, say, like this, okay, which way would this force act on this object? To the right or to the left? Yeah, so take your right-hand rule, aim your fingers away from you, aim your thumb down, and you should find that you get a force to the right. Like so, okay? If you flip the direction, you could get this to roll the other way. So you can actually make like a, I don't know if you want to call this like an electromechanical motor, sort of, similar idea to, any kind of magnetic motion. This is not how a motor works exactly, but a similar concept is there. Why? Because this is essentially like saying protons are flinging into this field, and they would be all bent off to the right, and so that is a tube of protons if you want, and they're all bent off to the right, and so the overall force aims this way. Okay, so that's what that's about. There's also this. Okay, so going back to the individual concept of positive charge firing into a magnetic field, Okay, so here's some amount of charge, Q. Okay, it could be a single proton or it could be a collection of charge. Q is measured in what units? Always charge. Coulombs. Coulombs. And it has some velocity, right? Some velocity in here. And we have a magnetic field of B Teslas. And again, we have this sine rule, right? So it depends at what, angle to the field we're flowing here. You get this other little handy guy here, QVB, or sorry, VB equals QVB, and again, that's sine theta, because only the amount of velocity that is at a right angle to the field experiences this force. So for example, a, I don't know, 2 microcoulomb sphere is shot into a 1 Tesla mag field at 1.5 times 10 to the 8 meters per second at 90 degrees to the field. Find the force on it. Well, straightforward. It's in this setup, so 2 times 10 to the negative 6 coulombs. Velocity, oh, we got this thing flying fast. And B, we said was 1t, and sine 90 is just 1, so we just put a 1 at the end. Let's see what we get. No calculator necessary for this. 2 times 1.5 is 3. 8 plus negative 6 is 2, so we should get 3 times 10 to the 2 newtons. So the reason that we do an example like this is because there's actually, as part of like particle accelerators, there are detector units that use this exact principle. And there's ways to visualize the pathways that charged particles take. So if you say accelerate particles at each other, like they could be like, protons, which are part of a group called hadrons, okay? And if you were to collide hadrons, and you were to do it in like a large accelerator, you might have a large hadron collider. And when these hadrons smash together, whatever they're made of fires out of them at like high speeds. Now, if you do this in a magnetic field, so you have these smashies happening right in the middle of something like this, okay, those particles might come winging out, and they might go into like swirly patterns, depending on a few things, right? So if they're light and slow, but highly charged, they might follow tightly coiled pathways, right? And whether they're charged positively or negatively, they're going to spin in different directions. Right. So you might be able to work out some properties, like what kind of charge this had, what its momentum was, maybe not directly its mass, but its momentum, right? Because there's a velocity vector here. And you've also got the concept, right, that these forces could be FC, right? This magnetic force could be creating a centripetal force on these things, right? So you can start to work out, after the smashy happens, what was actually inside these guys based on what kind of coils they take. So this might be called a bubble chamber. And we can actually find pictures from inside things like a bubble chamber and see what they would actually look like once they've been developed. Now, I don't know exactly how this is done nowadays. I think bubble chamber technology is a little bit older, but I know there are detectors like the Atlas detector and so on the new big collider that work more or less on this principle. They figure out, but I think they do it in 3D, the way that all of these things go. But I'll grab a bubble chamber shot for you so you get an idea of what this might look like. And you might be asked to do some math with this, right? You might be asked to say, this is equal to this. So you could have mv squared r is equal to qvb sine theta, right? And you could be given some of this information, and you could make these things equal to each other. What if we were solving for r here? Well, you might find this. What would you find? R equals mv squared over qvb. And actually, for the most part, probably you're dealing with 90 degrees, so that's just going to be irrelevant. And then you're going to cross one of those off, so you might end up with this. Nope, that's not right. Sorry. Yep, QB. Math is hard. QB. Okay? So there's something else that's interesting. So let's look at one of these bubble chamber pictures and unwrap it. Okay, and so here's that kind of bubble chamber picture we were sort of looking for. Okay, so each type of particle that comes out of one of these collisions is going to have its own signature pattern, depending on which way this magnetic field is aiming, and how strong it is, and et cetera, and physicists are able to mathematically work out some of the properties of the particles that come out of there. The higher the energy, the more interesting little particles seem to blast out of these things.